Assalamualaikum. My name is Muhammad Haziq bin ZAINUDEN with matrix number DD2020376. So my group will be presenting about an event of aircraft incident which is related to aircraft system malfunction or problem. So the topic we will discover is the Lion Air Flight 610.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Najwan bin Muhammad Salam. My matric number is DD2040139. Okay, for my part for introduction. On 29 October 2018, Lion Air Flight 610 crashed into the Java Sea just minutes after takeoff, killing all 189 people on board. This tragedy revealed serious flaws in the Boeing 737 MAX design, pilot training, and regulatory oversight. As the result, the aircraft was grounded worldwide. The key lesson is from this accident is clear. Aviation safety depends on transparency, proper training, and strong regulation to prevent future disaster. Okay, moving on. Now this is the Lion Air Flight 610 CVR and the animation of the tragedy. Okay, moving on. Now this is the Lion Air Flight 610 CVR and the animation of the tragedy. Okay, moving on. Now this is the Lion Air. Alright, for the purpose of this project or the objective of this project is to understand the aircraft system that is involved in this aircraft crash incident. First is to study the historical background of the aircraft crash for complete understanding. Secondly, to examine the aircraft accident resulting from aircraft system malfunction. And lastly, to analyze safety measures implemented to mitigate the recurrence of similar incidents in the future.
So right now we're talking about the history of airlines, which is the Lion Air. So for the airline background, it was founded in 1999 and operations began in the 2000s. It is a LCC, which is a low cost carrier, and it was one of the biggest low cost carrier in Southeast Asia. So from network, it went from high frequency to point routes, and it focused primarily on domestic with regional and international. So let's talk about the safety and operational history pre-flight 610. It had recorded multiple safety related incidents, runway excursions, hard landing, recurrent technical issues, especially in the AOA sensor. Incidents drew attention from multiple aviation authorities that it raised concern over, as well as maintenance quality, crew training standards, organizational safety culture, and lastly, regulatory compliance is maintained, but operational risks persisted. Next, we're going to talk about the history of the aircraft. So, first of all, we have operational and technical issues. Now, the aircraft has a high aircraft utilization and time pressure limited effective to troubleshooting, and it has recurrent airspeed and altitude discrepancy reported, which is no signal, no signage for airspeed and altitude, giving mostly wrong data, as well as the aircraft continued to be released even though it has repeated faults in the service, especially in the AOA sensor. Now, speaking of the AOA sensor, we're going to talk about the AOA, which is the angle of attack sensor issues. Now, the AOA sensor was replaced prior to the accident. So, before the accident, the AOA sensor was already experiencing multiple technical issues, so they replaced the AOS sensor with a new one. But they thought it was a new one. It was an old one that was refurbished. The replacement sensor was supplied by Extra Aerospace, which from the US, and investigation found out the sensor was likely miscalibrated before the installation. around 20 degrees to 25 degrees. Sorry, around 20 to 25. Now, there's no functional test conducted by maintenance before return to service. So basically, what they did is they put on the AOA sensor, the new one, and they didn't conduct any second, third testing, despite being a lot of faulty technical issues towards the AOA sensor. They just one test and then they're like, okay, let's put this back into service. When they're supposed to uh, constantly checking the sensor and the calibration because it has too much or too many faulty issues. Now, events prior to the accident flight. Now, the previous flight experienced enormous sensor data and abnormal flight control behavior. Now, maintenance actions were taken, but the root of the cause was not resolved. They just try to fix it overnight, and they ignored a lot of I would say a lot of steps to making sure that the AOA sensor is functional, fully functional. Now, the faulty AOA data triggered the repeated MCAS activation, which led to the loss of the aircraft control on Flight 610.
For this section, I will discuss the main causes of the Lion Air Flight 610 crash, focusing on the system failure, human factors, and organizational weaknesses. The first and initiating cause of this crash was the faulty angle of attack, or the AOA sensor. The AOA sensor, which was installed on the aircraft, had been incorrectly calibrated after maintenance. As a result, it continuously transmitted false high angle of attack data to the aircraft system. This incorrect information misled the flight control system into believing that the aircraft was approaching an aerodynamic stall, even though it was flying normally. The faulty sensor input became the starting point of the accident sequence. This leads to the malfunction of the maneuvering characteristics augmentation system, or the MCAS system. This system was designed to automatically command the nose down stabilizer trim when a high angle of attack is detected. Due to the faulty AOA sensor, the MCAS system activated repeatedly and unnecessarily, which each activation trimmed the aircraft nose down, forcing the pilots to continuously counteract the system. Despite the efforts, MCAS kept reactivating, progressively reducing the aircraft's controllability and contributing directly to the crash. Another critical cause of this crash was a single sensor dependency in the system design. MCAS relied on the output of only one AOA sensor at a time, without cross-checking data from the second sensor. This lack of redundancy meant that a single sensor failure was enough to trigger repeated incorrect system actions. In aviation safety design, critical systems are expected to be fault tolerant, and this absence of redundancy significantly increases the risk of catastrophic failure. In addition, the automated flight control system was given excessive authority. The MCAS had sufficient authority to move the horizontal stabilizer beyond what pilots could easily counter using manual control inputs. As the aircraft speeds increases, the aerodynamic forces made manual correction even more difficult. This excessive system authority allowed automation to override pilot control, contributing to the loss of pitch control of the flight. The situation got further worse by a lack of pilot awareness and inadequate training for the pilots. The pilots that was operating the Boeing 737 MAX were not fully informed of the existence of the MCAS system. The system was not clearly described in flight manuals, and simulator trainings on MCAS failure scenarios was not provided during the flight simulator trainings. As a result, the flight crew was unable to quickly identify the MCAS as a source of the problem and take appropriate corrective actions. The next cause is the maintenance and organizational deficiencies, which was also an important cause of this crash. The faulty AOA sensor was not properly tested after replacement, indicating weaknesses
in maintenance, procedures, and quality control. Furthermore, the aircraft had experienced similar issues on previous flights, yet it was returned to service without a complete resolution for the problem. This reflects shortcomings in maintenance oversight and organizational safety management. Finally, the certification and regulatory oversight failures contributed indirectly to the accident. During the certification of flight Boeing 737 MAX, changes to the MCAS system were not subjected to sufficient regulatory scrutiny. Parts of the certification process were delegated to the manufacturer, resulting in reduced independent oversight. This allowed a critical flight control system to enter service without adequate redundancy, transparency, or proper pilot training requirements. In conclusion, the crash of Lion Air Flight 610 was not caused by a single failure, but a chain of interconnected technical, human, and organizational factors that was aligned to produce this catastrophic outcome.
Right. Next, we will go to action, regulation, or safety practices that was ignored or violated during the crash. The first one is MCAS omission from manual and training, which is one of the most significant failures. Was that Boeing did not disclose the existence and detailed operation of the MCAS to the pilots. Uh, According to the investigation conducted, pilots that fly 737 MAX aircraft were unaware of the system. When they don't know that the system exists in the first place, so they could not interpret or deal with its behavior effectively during multiple inadvertent activation. So they don't know how to react when the system take control of the aircraft. This omission violated the principle that pilot must be fully informed of the critical flight control system and how to handle their failures. The next one is over reliance on a single angle of attack sensors, where the original MCAS design relied on just one angle of attack sensor, where safety standard generally require the redundancy for system whose failure could lead to catastrophic outcomes. Yet MCAS was certified without such redundancy, which is, as we all know, in aircraft construction, redundancy is important because if one system fail, there is a backup system that could activate in order to prevent a crash or serious incident to happen. The certification process accepted this despite widely understood safety engineering practices favoring multiple sensors for critical functions. So this is clearly a violation. The next one is inadequate maintenance or reporting. On the accident aircraft, the new angle of attack sensors has been miscalibrated after installation, and maintenance reporting failed to catch this prior to the fatal flight. Problems reported in previous flights were not fully documented or acted upon, meaning that the crew and the maintenance team lack complete information, which is a violation of proper safety reporting and also maintenance procedures. So also leads to clearly a violation and safety practices that has been ignored. So also leads to fatal crash. The next one is issue in airline operation and procedure, where Lion Air internal maintenance practice were criticized for not thoroughly diagnosing repeated issues with airspeed and sensor reliability prior to the crash, meaning that the airline itself ignore all this warning. So, and then finally, it led to the fatal crash. Investigators also suggested that the actual flight crew did not follow some appropriate checklists as precisely as required, contributing to loss of control. And the checklist is also important to be checked, to be followed precisely, so that we know we check that system is 100% functioning at every step of the checklist. The last one is FAA oversight shortcomings, where review report found that FAA's oversight during the original 737 MAX certification process was inadequate. In particular, the agency delegated much of the certification work to Boeing through its Organization Designation Authority (ODA) program, and then the FAA didn't fully understand MCAS behavior, even though the engineers eventually realized its potential hazard only after the crash. So there's also parts of FAA that caused to the crash where the FAA did not fully uh, understand the MCAS behavior, and then they still uh, approved this aircraft to be certified for operation. The next one is safety action and regulation implemented after the crash. So after the Lion Air flight 610 and the subsequent Ethiopian airline flight 302 crash, the Boeing redesigned the maneuvering characteristic augmentation system, which is MCAS, the software implicated in both accident to make it safer and less likely to trigger based on a single faulty sensor. The MCAS now compare inputs from two angle of attack sensors and will not activate if they disagree. And angle of attack disagreement indicator was added for pilot awareness so that they're aware if there is an disagreement in both angle of attack sensors, and also MCAS will only activate once per event and has limits that pilots can override more readily. These changes were certified by regulators before the 737 MAX was returned to service. Next one is Emergency Airworthiness Directive and Pilot Procedures. Shortly after the crash, the Federal Aviation Administration, which is FAA, issued an Emergency Airworthiness Directive requiring operators to adopt procedures addressing uncommanded nose down trim, the runway stability condition, MCAS could cause, and Boeing and regulators issue flight crew advisories updating flight manuals and checklists, including how to recognize and respond to MCAS related issue, like the like the runway horizontal stabilizers. The next one is Emergency Worldwide Grounding and Certification Reviews Directive and Pilot Procedures. The 737 MAX fleet was grounded worldwide in March 2019 after the second fatal crash, which is the Ethiopian airline flight 302. Underscores that the MCAS issue was systemic. During the grounding period, regulators consist of FAA, EASA, CAA worldwide conducted a comprehensive review of the MCAS design, pilot training, maintenance, and also the certification policies before allowing the aircraft to fly again. Next one is enhanced training requirements. Regulators updated the pilot training standards requiring specific simulated scenarios and procedures for MCAS-related failures. A big change from the earlier practice where basic 737 MAX trainings did not include MCAS failure scenarios. The last one is reform in FAA oversight and certification. Following political and congressional scrutiny, the FAA began implementing reforms intended to improve transparency and oversight in aircraft certification process, such as enhanced oversight of delegated work and also broader use of safety management system across aviation.
So for the conclusion, this accident shows how several weaknesses can come together and lead to a serious outcome. In this case of Lion Air Flight 610, the main technical issue was the MCAS system, which relied on data from only one angle of attack sensor. So when the sensor provides incorrect reading, MCAS repeatedly pushes the nose of the aircraft downward, making it extremely difficult for the pilots to regain control. So from this accident, there are three important lessons to be learned. The first Aircraft system must be designed with improved redundancy and clear warnings so that a single sensor failure cannot lead to a loss of control. Second, pilot must receive complete and effective training on all critical systems, including how those systems can fail. And finally, a strong safety culture must be maintained among airlines, manufacturers, and regulators to ensure risk and identify early and manage properly. In conclusion, this accident highlight that aviation safety depends not only on technology but also on training, communication, and shared responsibility across the entire aviation industry.